Hey, we're going to talk about conservation of momentum and momentum in general. Um, so this is chapter 11, it covers a new concept of impulse and momentum. So just to get right through it, linear momentum, we're going to define it as the mass of an object times its velocity. So momentum, the symbol is p, it is a vector, and it inherits the direction from velocity. So this is kind of just showing you as a diagram form here, right? So here's the velocity of an object, you'd multiply by its mass, so the vector length would increase, and that's your momentum. So it's in the same direction as velocity. It does not have its own units. Its units are just kilogram, meter per second, right? So it's just the mass times velocity. So Newton actually formulated the second law, F equals ma, that we've used it in this form, but he actually formulated it in terms of momentum. And we can see how these are equivalent if we just do some substitute in for acceleration, change in velocity over change in time. So that's here. And then if we bring that mass inside the delta, right? So just mv final minus mv initial would be what this expression is, divided by delta t. And like I said, this is our expression for momentum. Okay, so we can say that if there's a net force acting on an object, it will experience a change in momentum. And then just to show you the equivalent set of definitions if we're actually using calculus here, right? So all the deltas become differentials. Okay, so those are equivalent. And so for the most part in this course, right, if we have a change in momentum, it's going to be due to a change in velocity, but you can have examples where the mass changes as well, and you get a change in momentum that way. Okay, so there's another concept or quantity called impulse, and we can see what this is just from rearranging this equation. So here's our net force is change in momentum over time. If we multiply both sides by delta t, we get an expression for the change in momentum, and it's the force acting on the object over the time that the force is acting. Okay, so this is basically for a constant force, when we look at these deltas, right? So this change in momentum gets a special term called impulse. Okay, so impulse, the symbol for that is J. It is really just a change in momentum. And again, it's a product of the force acting on an object times the time, the net force, right, times the time that force is acting. So just a couple of check questions here. Is impulse a vector or a scalar? It is a vector, right, just like momentum. And its units are going to be the same as momentum. So they are kilogram meter per second. Okay. So here's an example problem. So what is the cart's change in momentum? So let's go to so it's initially going to the left at 2 meters per second. Write that down. I'll draw the picture here. And then it afterwards it hits the wall and bounces off, and then it's going to the right at 1 meter per second. Okay. And the mass is 10 kilograms. Let's take our debug. So we are given that the mass is 10 kilograms. We're given V initial, let's say, is minus 2 meters per second because it's going to the left, and V final is 1 meter per second. Okay, so we'll put our coordinate axis, looks like that. So it's all in the x direction, right? And negative means it's going to the left initially, and then positive means it's going to the right. Okay, so what is the change in momentum? Change in momentum is just final momentum minus the initial momentum. And again, it's all just in the x direction. So this is m v final x minus m the initial x. Okay, so we have our mass here, right, 10 kilograms. V final is 1 meter per second. And then we have minus our mass again of 10 kilograms, and our velocity is negative 2 meters per second. Okay, so we get 10 kilogram meter per second plus 20 kilogram meter per second gives us 30 kilogram meter per second. That's our change in momentum. And that is also equal to the impulse, J. Okay, So there we go. We got it right. Excellent. Okay, if the force is not constant, then we would calculate impulse as the integral of force versus force times dt, right? So what that means graphically is that this integral is just the area under the force versus time graph. So if we think about, we want to know what the impulse is, and we have a plot of force versus time, the shaded area in red is equivalent to the impulse. It's the area under the force versus time graph. So it's okay if you don't know how to do the integration. We can always do it graphically. So obviously for this picture you can't, but we would give you, like a triangle or a square or a rectangle that would be easier to figure out the area from. Okay, and you don't want to confuse impulse or change in momentum with force. So this is a picture from Paul Ewart, who's written the great conceptual physics book. And just thinking about what it would feel like to be if a boxer is getting punched in the face. So a nice thing to think about. But on the left, the boxer is going to lean back away from the punch a little bit so that the time of contact increases. And in the right, the boxer leans into the punch. So if we look at what happens in terms of change of momentum, the change of momentum is the same in both cases, right? The punch is coming in at some speed and it stops on the person's face. But on the left side, the time is big, right? Because you're leaning back and increasing the time of that the punch is in contact with your face, right? So T is big, therefore the force is smaller, but you get the same change in momentum. On the right, you're leaning into it so that the change of momentum is transferred over a small amount of time and you get a bigger force. Okay, but it's the same change of momentum. So the same concept applies to airbags, right? Where you have this balloon basically that you're going to hit into as you're stopping quickly in an accident, and it's trying to increase the time over which your momentum is changing, right? So normally you would have just gone straight and maybe hit the windshield or hit the dashboard, whereas if you hit the airbag, you start slowing down over a longer period of time. Okay, if the system is isolated, momentum is conserved. So we can see this mathematically from our equation, right? That says net force produces a change in momentum. Again, change in momentum is our final momentum minus the initial momentum. If this net force is zero, right, then this difference is also zero, which tells us our final and initial momentum are the same. And here's a case where we have a cannon, again, another nice cartoon from Paul Ewart, where the cannon is launching a cannonball. So initially the system's at rest, right? The momentum is zero. After the cannon fires, the ball gets carried off to the right with a very large velocity, and the cannon itself actually kicks back. So it's got a big mass and kicks back with a smaller velocity. So again, we have big mass times small velocity, small mass times big velocity. Those are will end up being the same value, and they'll be in opposite directions. So when we add up the vector, we get zero. Okay, and whether we say momentum is conserved or whether there's some external force depends on what we define as our system. So here's just a comparison of a ball dropping toward the earth in two different ways we can think about our system. In the first, we're saying the system is the ball. And in that case, then the ball is experiencing an external force from gravity, from the gravitational pull from the earth. Okay, and so that's going to change the ball's momentum. And then if our system here is the earth and the ball, then the total momentum of the system is going to be conserved, right? So the ball is going to gain some momentum. The earth is so big that we don't really actually see its corresponding change in momentum, but the system momentum will be the same. Okay, momentum is conserved in all collisions. It's really useful when we're trying to analyze collisions. Whenever you see a collision, you should think, I need to apply conservation of momentum, right? Collision, conservation of momentum. Okay, so there are three different types of collisions. So the first one is elastic, and that's where two objects come together, or even three objects, and they bounce off each other. But it's a very clean interaction. Elastic, so they maybe like deform momentarily, but they spring back, and there's no energy loss in the system. So momentum will be conserved, and energy is conserved. And this is a picture showing two balls coming together. They collide quickly, and then they move apart from each other. Okay, inelastic is the other extreme where two objects come together and actually stick together. So in all of these collisions, momentum is conserved, right? So collision, momentum, conservation, collision, momentum, conservation. When they stick together, though, energy is not conserved, okay? So some of this energy will be lost into deforming the shape of the two objects that collide. You may get thermal energy created, and you may have sound energy that's emitted. So all of those things go into, so the kinetic energy wouldn't be conserved, right? Okay, and then the opposite of this inelastic collision is an explosion, where you'd start with one object that explodes and two objects get shot out from it. Again, momentum is conserved for the system, but energy, kinetic energy, is not. Okay, so let's do our another example. We have just to look at a collision here. So we have one train car heading toward another. This one is at rest, and these are actually how train cars will link up. So they'll bump into each other and stick together, right? They get hooked together. So if one is moving with the velocity of the initial, this one's at rest initially. The question is, how fast is it moving when they are, after they join together? So what type of collision is this? They're sticking together, so it is inelastic collision. So let's look how we would use conservation of momentum to solve this. So we always want to go and try and think of these before and after pictures, right? What does it look like before? What does it look like after? And then we will do our momentum final or after is equal to the momentum before or the initial momentum. So in this case, we have two objects, so we can write the momentum after is the mass times its final velocity, and then mass 2 times the final velocity. And then the same thing for the initial, right? M1 times its initial velocity, M2 times its initial velocity. The initial velocity here is 0, right? And the masses are the same mass. Okay, so that's good to know. So afterwards, these two objects are going to move with the same velocity. So that's a key thing to keep in mind when you're looking at an inelastic collision. So they stick together and move with some final velocity. Both masses are the same, right? So the final momentum just simplifies to 2m times the final velocity, and that's equal to m times the initial velocity. And then if we actually solve then for the final velocity, we see that it's going to be 1/2 of the initial velocity. Okay. And that problem didn't have any numbers, right? It was just algebra. Okay, the whiteboard problem you guys are going to do. Okay, so let's do this example of radioactivity. So we have a uranium-238 nucleus is radioactive, and it's going to spontaneously disintegrate into a small fragment that's ejected with a speed of 1.5 times 10 to the 7. So let's write that down. Velocity of the fragment is 1.5 times 10 to the 7 meters per second, and a daughter nucleus that recoils with a speed of 2.56. So the velocity of the daughter is 2.56 times 10 to the 5th meters per second. And then find what are the masses of the fragment and the mass of the daughter. Okay, so let's go over. This is an example in night, so you can always check that again. Look at it in your book. Okay, so this is what we were given. And also that the mass of uranium is 238U, right? So that's the atomic unit, which is basically the mass of the proton. It doesn't ask for the mass of the fragment and daughter in kilograms, so I'm just going to leave my mass in atomic in atomic mass units. Okay, so let's say this is our uranium before, and then there's a radioactive decay, so we get a little fragment piece that shoots off with a very high speed. Right, this is almost, 3 times 10 to the 8 is the speed of light, so this is like a significant fraction of the speed of light. Okay, and then whatever is left here, the daughter, right, that's the mass of our daughter, that's going to get sent back in the opposite direction with a lower speed. Okay, and then we want to find what these two masses are. Okay, so we use our conservation momentum. So this is before, right? This is our before picture, and that's our after. This I should put before here. Okay. Again, good to draw the before and after so we know what we're talking about. Momentum's a vector problem, so I should put in my coordinate axes here, x and y. Okay, and then I'm going to write my final momentum is equal to my initial momentum. Okay, and everything is just along the x axis as I've drawn it here. So my initial momentum is 0, right? Nothing's moving. And then afterwards, I have my fragment is moving to the right. So I'm going to have my M fragment times B fragment, and then my daughter, the big nucleus that's left behind, is going to be moving to the left in the picture I've drawn. So M daughter, B daughter, and that's going to be equal to 0. Okay, so we only have one equation so far. We have two unknowns. So the other thing that we know is that mass is conserved. So mass conservation tells us that the mass that we started with, so the mass of uranium equals the mass of the daughter plus the mass of the fragment. Okay, and we do know that one. All right, so let's get these on either side from each other. So we have the mass of the daughter times the velocity of the daughter is the mass of the fragment times the velocity of the fragment. And then here I can solve for the fragment, let's say. So the fragment is going to be the mass of uranium minus the mass of the daughter. And then I'm going to plug that in over here. So the mass of the daughter, speed of the daughter equals mass of uranium minus the mass of the daughter times the speed of the daughter. Nope, this is fragment. I don't know if you guys caught that. Hopefully you did. Okay, so mu times the speed of the fragment minus the mass of the daughter times the speed of the fragment equals the mass of the daughter times the speed of the daughter. So I'm going to solve for this first, right, because I know uranium. So I'm going to bring these over, so I get the mass of the daughter times its speed plus the mass of the daughter times the fragment speed equals the mass of uranium times the fragment speed. And factor out the mass of the daughter. Okay, and then I get mu v up there. I'm going to divide by the speed of the daughter plus the fragment. So I get that the mass of the daughter equals the mass of uranium, so that's 238U, times the speed of the fragment, 1.57, 1.5 times 10 to the 7 meters per second, and then I divide by the sum, 2.56 times 10 to the 5th meters per second, plus 1.5 times 10 to the 7 meters per second. And if we do that out, we get 234U for the mass of the daughter. We box our answers, so it looks nice. And then we can find the mass of the fragment by looking back up here, right? So the mass of the fragment equals the mass of uranium minus the mass of the daughter. 238U minus 234U equals 4U, the mass of the fragment. Okay. Right, so these are all the elements of a nice presentation, right? So you guys should be setting up your homework problems like that as well. Okay. Yeah, you've got it right. Okay, well, last thing we're going to do is this two-dimensional collision. Okay, so here's a case, and this is actually relevant. You guys are going to do this very similar type of problem in lab called an accident reconstruction. Okay, so let us look at this problem. So we have two cars that are coming together and they're perpendicular to each other. Okay, so we have car 1 here is 1,500 kilograms. Car 2 here is 3,000. So I'm going to write that down. So M1 is 1,500 kilograms. M2 is 3,000 kilograms. We know that V1 is 25 I hat meters per second. The initial 1. The initial 2 is 20 J hat meters per second. Okay, and then we need to find the momentum and velocity of the car. So afterwards, so they're going to stick together. So P final and V final. Okay, so let's go back to our camera here. So I'm just going to do balls for cars, right? So this is M1. It's with its V1 initial, and then we have coming down this way a little bit bigger car. This is M2, V2, right? That's our before picture. And then afterwards, they're going to be moving together. V final, at some angle, let's say, and it's going to be the combined mass m1 plus m2. Okay, so this is a vector problem. I'm going to put my coordinate axis in the regular way, so this is going to be my x, and that's going to be my y. Okay, so this is the first time we've had to worry about the full vector nature of momentum, right? We've just done one-dimensional problems. Okay, so we're going to do final momentum equals the initial momentum. Okay, and then so this is going to be the momentum for one, its initial momentum, and the momentum for the second car, right? And then this is just going to be the combined. I'm actually just going to swap sides if you guys don't mind. We'll put the P final over here. Okay, so for one, right, our momentum is mass times velocity. So we could, write another vector equation if we want, right? But m1 v1 initial plus m2 v2 initial equals m1 plus m2 times v final, which is a vector, right? Okay, so now we can put in our column vectors. And remember, whenever we have a number like mass times the vector, it goes and just multiplies both components of it. So we get m1 v1 initial x, m2 v1 initial y. Right, remember our column vectors, we're just going to put our x in the top row and y in the bottom. And then we have m2 v2 initial x, m2 v2 initial y, and that's going to be equal to m1 plus m2 v final x, m1 plus m2 v final y. And I know a lot of these terms are zero. I'm just putting it all in here for completeness, okay? So if we look now at v1, right, it has an I component but not a j. So y is 0 for v1. And then for v2, it's got a y component but not an x component. So that is 0 for the second car. Okay, so we have now two equations, right? So we have the momentum equation for the x direction and the y direction. So we can just bring those out here. So x says m1 I'm doing it backwards, but v1 initial is going to be equal to m1 plus m2 v final x. So that's one equation. And then for y, we get m2 v2 initial equals m1 plus m2 v final y. Okay, so we can actually find now what v final x is, right? So we can get v final x is m1 v1 initial divided by m1 plus m2. And v final y is m2 v2 initial divided by m1 plus m2. Okay, so let's see what we get. All right, so m1 is 1500 grams. It's going at 25 meters per second. And then we divide by total mass, which is 4,500 kilograms. 1, 2, 3. So let's get our screen up here. All right, so we have 1,500 times 25 divided by 4,500. Okay, so we get 8.33 meters per second. And that's going to be, in the I direction. And then v final y is going to be m2. So that's 3,000 kilograms. V2 initial is 20 meters per second. And then again, we're divided by the total mass, 4,500 kilograms. So we will do 3,000 times 20 divided by 4,500. So final x, v final y equals 13.3 meters per second. Okay. And so if we want to write what our v final is in column vector notation, right, it's 8.33 meters per second and 13.3 meters per second in the y. And if we want to do our momentum, we would just take these and multiply by the mass. So it is, which actually just happens to be the numerators of these, right? I could have just not done any algebra and added those up. Okay, so in the x direction, we have 1,500 times 25 equals 37.5. Oh, sorry, guys. Should have told me I was going off the page. 37,500 kilogram meter per second. And then over here for the y direction, it would be 3,000 times 20. Okay. If the problem also asked for like the velocity, the direction of velocity or direction of momentum, they're actually in the same direction, right? We talked about that. This is the vector. But we could figure that out as well, right? So this is saying that I have an x velocity of 8.3 and I have a y of 13.3. And I could find my hypotenuse and that angle. Right, so v final would just be the square root of v final x squared plus v final y squared. And theta, I could do my inverse tan of v final y over v final x. This problem didn't actually ask for it specifically in terms of magnitude and direction, but I just want to show you in case you need to calculate that. Right, it's just vector stuff that we've been doing since chapter 3. Okay, that's it for momentum. Thanks for stopping by.